Hi, this is the third lesson in electricity and mainly focused on Edexcel, Cambridge, and International Baccalaureate syllabuses. The video link for the first two lessons are given in the description of this video. You can go through them if you like. Right. Okay, during my first two lessons, I discussed few equations related to electricity. In the first lesson, I discussed two equations. They are Q equal IT. I got it from the definition of current. And the transport equation I equal NAEV. During my second lesson, I introduced few more equations, and they are the potential difference across a component that is given by W equal Q into V, where Q is the amount of charge flown through the component, W is the work done to move charge Q through the component, and V is the potential difference across the component. And the electromotive force, that is a property of a power supply, that is the amount of work required to move 1 coulomb charge through through a complete circuit, is defined as the electromotive force of the power supply. It is given by W equal Q times EMF. EMF is denoted by epsilon. Then we learned about the definition of resistance, R equal V over I. So we normally write the potential difference across the component as the subject. So V equal I times R. Then the resistance of a component is given by, it depends on the properties of a, say for example, not a component, the resistance of a wire is, it depends on the properties of the wire. That is, resistance of a wire is directly proportional to the length of the wire and inversely proportional to area of cross section. So R equal rho L over A, where rho is the resistivity of the material that is constant for a given type of material at constant temperature. But for conductors, when temperature increases, resistivity will increase. For semiconductors, when the temperature increases, resistivity, which is rho, will decrease. Then we learned about the power dissipation or power loss in a component, that is given by P equal VI, or P equal I squared R, or P equal P squared over R. Then the power generated by a power supply is given by P equal EMF times the current flow through the power supply. Okay, so these are the equations we learned during the first two lessons. So in this lesson, I'm going to discuss a few questions related to these equations, and the questions are uploaded. You can download from the description of this video. Okay, the first question, you can get these questions from the description I uploaded. You can download it from there. First question, how many joules of energy does a 9-volt battery supply when a charge of, first question, first part, when a charge of 15 coulomb passes through it? Okay, so the first question, how many joules of energy does a 9-volt battery supply when, the first part, a charge of 15 coulomb passes through it? So first question, first part, I can use W equal Q times V. The amount of charge flown through that is 15 coulomb, and the potential difference across it is 9. So that will be 135 joules. Answer for the first part of the first question. Second part of that question, a current of 0.6 ampere flows through it for 2 minutes. I need to find the energy supplied by the battery, which has EMF of 9 volt. So second part, you can download the questions from the description, right? I'm not writing the question. I just read the question because you can download it from there. Okay, so I need to find first the amount of charge flown through it. Q equal I into T. So the current flow is given as 0.6 amperes and the time taken is 2 minutes. So 2 into 60 seconds. Find the amount of charge flown through it. That will be 0.6 into 2 into 60. That will be 72 coulombs. So 72 coulombs is the charge flown through it. Now I can use W equal QV or Q times epsilon. Either one I can use, same answer you will get it. So Q means 72 into 9. So that will be 648. 648 joules. Okay, second question. A power supply of a torch bulb, the power of a torch bulb is 0.75 watts. What do you mean by power of a torch bulb? That means the power consumed by the torch bulb is 0.75 watts. Yeah, that's what we call power of a torch bulb. The power consumed by the bulb is 0.75 watts, and the total power dissipated in the form of light and heat, that also 0.75 watts. That's the meaning of power of a bulb. And the current flow through it is 0.3 amperes. So first part, find the resistance of the bulb. So I can use this equation, P equal V squared over R. I know the power of it. The question is the resistance. I know the current, so I can use the second equation, P equal I squared R. Second question, first part, I can use P equal I squared R. The power is 0.75. The current flow is given as uh, 0.3 ampere. So 0.3 squared into R. Find the R. So resistance will be 8.33 ohms. Second part of second question, find the voltage applied across the bulb. So that is V equal IR. I can use simply V equal IR. So current, I know that 0.3, resistance 8.33, correct, right. So find the voltage across it. So that will be 2.5 volt. Okay, third question. Energy transferred by a generator is 0.3 megajoule. That is 0.3 into 10 to the power 6 joule. That's energy transferred. Means that's energy generated by the electrical generator. Is it? When deriving a current of 2.5 ampere for 10 minutes. So the current flowing through the generator is 2.5 ampere and it's used for 10 minutes. And the total energy generated by the electrical generator during 10 minutes is 0.3 megajoule. How much charge passes through the generator during this time? Okay, so how much charge passes through the generator during this time means the first part, I can find Q equal IT. So that's the amount of current into time. Current we know that is 2.5 amperes and the time 10 minutes. So I should convert to seconds, multiply by 60. So that will be 1500 coulomb. That's the amount of charge flown through the electrical generator during 10 minutes. Second part, find the calculate the electromotive force of the generator, EMF, that is electromotive force of the electrical generator. So I can use this equation, W equal Q times EMF. So for electrical generator, so that's the work done means that's the total energy transferred through it. So W is given, that's the total energy 0.3 10 to the power 6. The amount of charge flown through it is 1500 into EMF. Find the electromotive force across the generator. Okay, so that will be 200 volt. Okay, so the next question, fourth question. A copper track on a printed circuit board is 8.5 millimeter wide, 2 millimeter thick, and 4 centimeter long. Resistivity of the copper is given 1.7 to the power minus 8 ohm meter. First part, calculate its resistance. So we know the length, that is 8.5 millimeter, and the width I know 2 millimeter. 2 millimeter is the thick and 4 centimeter is the length. 4 centimeter is the length, and width and thickness also I know that. So if I think about the copper track, I can draw like this. Okay, so I can draw the copper track like this: 4 centimeter length, 8.5 millimeter width, and 2 millimeter thickness. So the area which is perpendicular to the current flow is this area. And we know the equation to find the resistance. First part, R equal rho L over A. So resistivity is given 1.7 10 to the power minus 8. The length is given 4 centimeters, so 4 into 10 to the power minus 2 meters. Area of cross section is the area perpendicular to the direction of current flow, that is this area. So width into thickness, so 8.5 10 to the power minus 3 into 2 into 10 to the power minus 3 ohms. So if you solve it, you will get the resistance of the copper track. That will be 4 into 10 to the power minus 5 ohms. That's the first part answer. Second part, calculate the voltage across it when it carries a current of 25 milliamperes. So simply I can use second part, V equal I times R. So the current is given 25 milliamperes. So 25 into 10 to the power minus 3. And the resistance 4 into 10 to the power minus 5. So solve it. You will get the voltage across the copper track. Answer will be 1 into 10 to the power minus 6 volt. That is, I can say 1 microvolt. Okay, fifth question. A copper wire of length 4 meter has a cross-sectional area of 0.2 into 10 to the power minus 6 meter squared. Copper has 1 into 10 to the power 29 per meter cube free electron. So that is the charge carrier density. N is given. Resistivity of the copper also given as 1.7 10 to the power minus 8 ohm meter. First part, calculate the current through the wire when the drift speed of the electrons is 0.94 millimeter per second. Okay, so I need to find the current through the wire when the drift speed is 0.94 millimeter per second. So I need to use this equation, I equal NAEV. First, fifth question. First part, I equal NAEV. So charge carrier density is given, that is the number of free electrons per meter cube, 1 into 10 to the power 29. The area of cross section is given 0.2 into 10 to the power minus 6. The charge of an electron 1.6 10 to the power minus 19. You can get it in the data sheet of your question paper. And the drift speed is given 94 millimeter per second, 0.94 millimeter per second. So 0.94 into 10 to the power minus 3 meter per second. Solve it. You will get the current flow. So the current will be 3.008 amperes. Second part, a second wire with the same dimensions is made of a material that has a greater resistivity. Second part, calculate the potential difference across the wire. Okay, that's the third part what I read now. Second part, calculate the potential difference across the wire. So potential difference across the wire means I should use the equation V equal I times R. But I need to find the R first. I know the current through the wire, but I need to find the R first. So to find the R, second part, R equal rho L over A. So the resistivity is given 1.7 10 to the power minus 8. 1.7 10 to the power minus 8 is the resistivity. The length of the wire is given 4 meters. And the area of cross section is given that is 0.2 10 to the power minus 6. So this much of ohms, solve it, you will get the resistance. So that will be 0.34 ohms. Now you can use V equal IR for the wire. So current we found it 3.008 into resistance 0.34. So that will be the voltage across the wire. So that will be 1.023 volt. Okay, third part is something explaining type question. A second wire with the same dimensions is made of a material that has greater resistivity than copper. So same dimension, second wire has the same dimension as this copper wire, but it has the material, the second wire material has greater resistivity. That is given in the question. So what will happen? Greater resistivity, but dimension same means same length, same area of cross section, but resistivity is higher means the resistance of the second wire will be larger. Is it? Resistance of the second wire is going to be larger. Right, we'll see what's the question. The question says, explain how, if at all, the current will differ from that in copper wire when the same potential difference is applied across it. Okay, so the answer should be like this. I'm not writing it, but you can understand. You should say like this. Since the second wire has the same length as the first wire and same area of cross section as the first wire, but it has greater resistivity, the second wire. Therefore, according to R equal rho L over A, you should refer the equation, which equation we are using. According to R equal rho L over A, the second wire will have larger resistance than the copper wire. Right, so you showed it. Second wire has larger resistance. So resistance of the second wire is larger, right? Because resistivity is larger, L and A are the same as copper wire. We are comparing the both wires. Then they're asking about the current flow. And same potential difference is applied as whatever the potential difference applied across the copper wire, which is 3.0. We found the potential difference across the copper, that is 1.023. The same potential difference is applied across the second wire also. So then you should refer according to V equal IR. Since both wires have the same potential difference and the second wire has larger resistance, according to I equal V over R, the current flow in the second wire will be lower than the current flow in the copper wire. Okay, again I'll tell that. So first you should say, since the second wire has greater resistivity and the same dimension as the copper wire, according to R equal rho L over A, the second wire will have greater resistance than the copper wire. Then you should say, since the same potential is applied across the second wire, according to V equal IR, that is I equal V over R, since R is greater, the current flow in the second wire will be lower than the current flow in the copper wire. That should be the answer for the third part of this question. Okay, the same question, fourth part. So we showed that in third part of fifth question, I already showed it. So the current flow in the second wire will be lower than the current flow in the compared to the current flow in the copper wire. Now the fourth part of the same question, question number 5, you can read the question from the paper. You can download it from the description of this video. The number of free electrons per meter cube in this wire is the same as that in the copper wire. So that means both wires, both materials, the material of the second wire and the copper has the same charge carrier density. They are telling it. Compare the drift velocities of the electrons in the two wires. Okay, so I can use the equation I equal NAEV, right? Both have same charge carrier density, that is given in the fifth part. Both have the same charge carrier density. Both have the same cross-sectional area because both have the same dimension that is mentioned in the third part. So both have the same dimension means that means both have the same area of cross section. E is the charge carrier density, so same E. So when we consider both wires, both have the same charge carrier density, same area of cross section. E is the charge of an electron, that also same. But the current flow in the second wire is lower. Current flow in the second wire is lower. So all these three are same for both wires, but current flow is lower for the second wire. Therefore, the drift speed of the electrons in the second wire will be lower than the drift speed of the electrons in the copper wire. That's the answer you should say. You can simply say both, since both have same N, same A, and same value of E, and since the second wire has lower current, according to I equal NAEV, you have to refer the equation, according to I equal NAEV, the drift speed of the electrons in the second wire will be lower than the drift speed of the electrons in the copper wire. That's the answer for the fourth part of the fifth question. Okay, the sixth question. A 500 watts electric toaster operates from 230 volt main. First part of the sixth question, calculate the current in the heating element of the toaster. So we know the power of the electric toaster. That means the power dissipated by the electric toaster or the power consumed by the electric toaster. Both refers the same. That is 500 watts and the voltage across it is given 230. So calculate the current. So simply I can use P equal VI first part. So the power is 500 and the voltage across it is 230 times I. So I is equal to 2.17 amperes. Okay, second part. Again, it's an explaining type question. The heating element of the toaster is made of much thinner wire than the wire in its supply head. Okay, the coil. It's made of a thinner wire than the wire which is connected to the plug point, right? But both are made of the same material. So both are made of same material means both will have the same charge carrier density and same resistivity. So the wire which is the material which is used to make the coil and the wire which is used to connect the heating element to the plug point, both are made of same material. That means both will have same charge carrier density and same resistivity, but the coil is much thinner than the wire which is used in the supply cable. When same current flows through the both wires, so current is the same, in which of these two wires do the electrons have the greater drift velocity? Explain your answer briefly. So you can simply say drift velocity means we have only one equation, that is I equal NAEV. So second part you can use the equation I equal NAEV. Okay, simply we can say both have the same current because that's given in the question. Both are made of same material means both have the same M. E is the charge of an electron, so that will be the same for both. Yeah, whatever the wires. So we can say same E, but thinner wire means area of cross section is smaller. So for the coil, A of coil, the area of cross section of the coil is less than area of the cable. So when we compare both are going to have the same current, same N, same E, but the coil has smaller area. Therefore, the drift speed should be larger in the thinner wire in the coils. I can make the V subject if you want. V is equal to I over N A E. So I can say when I make the drift speed subject, both have same I, same N, same E, but thinner wire, that is the coil, has smaller area of cross section. Therefore, the electrons in the coil will have larger drift speed. That's the answer. Okay, so the electrons in the coil will have large drift speed. Okay, so that's the end of these questions. I hope that will be useful. Okay, so that's the end of the third lesson. We'll meet in the fourth lesson. Bye.